Right, good afternoon. What I'd like to look at today is energy changes in harmonic motion. I'm going to derive an equation that will give you the velocity of a harmonic oscillator, and also look at how energy is interchanged between kinetic and potential energy for certain systems. So to begin with, we're going to take the example of a simple pendulum again, and I'm going to draw it in three positions. We'll label this, I don't know, X, Y, and Z. Now, let's look at the energy interchange as this thing oscillates. So we'll have potential energy and we'll have kinetic energy. And we'll do the three positions, X, Y, and Z. Now, it should be fairly obvious that in position X, that all of the energy, we'll just call it total, is potential, and the kinetic energy is 0. At position Y, when the bob is moving, it has no potential energy at the minute, it's at its lowest point, so that will be 0, and the kinetic energy will be equal to the total energy. In position Z, it goes back to the starting position, it's just reversed, so we're only interested in magnitudes, so that will be total and 0 again. And the thing to remember is that assuming that we don't have any friction in the system, that the total energy is constant throughout a system. Now I know that's not really true because it will die down eventually. It'll have a bit of friction and stuff, but we're going to assume that that is the case for now. So that's the first thing that we need to bear in mind, that for a harmonic oscillator system, in the absence of damping with no friction, and we will look at damping some point next week, that the total energy is always going to be a constant. It's just interchanges between kinetic and potential. And that's true for any harmonic oscillator, mass on a spring, anything. It's going from potential to kinetic, back to potential, back to kinetic again. Right, moving on. What we're going to do now is derive an equation which you will be given, that should give us velocity. So I'm going to take another example. I'm going to do the mass on a spring, simple one like that, and obviously we're going to displace this by a certain amount x and allow it to oscillate. And we're going to ignore any friction effects. We're going to assume that the energy is constant and the thing is just going to bounce up and down. Now, from first principles, the potential energy of a mass spring oscillator can be given by 1/2 kx squared, which is a standard equation for energy stored in a spring. Now, the total energy, which I'll call it E total, this is going to be basically a special case of here where x equals the amplitude, i.e. max displacement. So when it's furthest away from its original position, then we can simply replace the x with a, because that is the amplitude of the oscillations, and we can rewrite that as 1/2 ka squared. Okay, now looking at another form of this total energy, the total energy is going to be given at any one point by the kinetic energy plus the potential energy of the system. And that's true for all points in its oscillations. You add the two together, you will get the total energy. At some points, one may be 0. At some points, they both may have a bit, maybe half and half, but that's how you calculate it. Let's just quickly rearrange this for kinetic energy. So kinetic energy is now going to be the total energy take away the potential energy. Now let's substitute some numbers in here and see if we can get an expression for this. So that's going to give me, first of all, the expression for the total energy, and I'm going to use this one up here. That's going to give me 1/2 ka squared minus 1/2 kx squared. That, of course, is the this first one, the potential energy at the top. Now, I can obviously simplify these two things down. So that will give me 1/2 k a squared minus x squared. Remember, A is the amplitude, and that is the point of maximum displacement. So it's not quite the same as X. It's the biggest value of displacement that we can get. Right, let's rewrite this guy, EK. That's going to be the kinetic energy of the system. So we can rewrite that as the kinetic energy equation, 1/2 mv squared. And that's going to equal this thing now. So that equals 1/2 k a squared minus x squared. I'm just going to do a bit of manipulation to start with. Obviously, we can get rid of the half straight away. We can multiply by 2 on both sides. But I'm also going to divide by m, so I'm ending up with an expression for v squared. So v squared will now equal k over m, and then all this governs the a squared minus x squared. Now, what we can do is, I know from the previous lesson that omega, in this case, is equal to k over m. That's putting it into the equation of the harmonic equation. Acceleration is proportional to negative displacement, and I can rearrange that, and I can substitute that in instead of writing k over m. So we end up with v squared is omega multiplied by a squared minus x squared. And sorry, that should be omega squared, my mistake. Omega squared equals k over m, so I'll just put the squared in there. Take the square root of both sides, and we end up with an expression for velocity. Velocity is now omega square root a squared minus x squared. And that is an equation that you will need to use. You'll be given it, obviously, like all A-level equations, but that is essentially where it comes from. And that gives me the expression for the velocity at any given point of a harmonic oscillator. All we need is the angular frequency, and remember this might be given by 2 pi f as well. The amplitude, A, take away the displacement. And this kind of makes sense. Let's do an extreme example of when it's at one end of its cycle. So A will be equal to x, then the velocity will be nothing, which makes sense because in a pendulum, for example, when the bob is right at the end of its swing, its velocity is nothing. And of course, its velocity is going to be a maximum when its displacement is nothing. So the a squared minus nothing will give you a squared. That will give you the maximum. So it does fit. It does seem to work. Now, all I want to do now, you can pause this if you want to have a closer look at this derivation, but I'm going to rub it out now. One thing that does come up quite often is how to plot a graph of the energy changes involved. So this is usually done as a rather strange graph like this, and we're going to have two lines. I did them in different colours, I think, to try and make it a bit better. One like that, and one like no, that's not a different colour. Silly thing. And one like this. Now you can see that if I were to add these two things together, then you would get the same amount. So basically, this is the total energy at the top, and all we've got with a harmonic oscillator is the interchange between the two. So this one might be it's going to be the kinetic energy, and this one is going to be the potential energy. So you can see I'm not drawing this quite right because I've left a gap there and there, but that's just me making a mistake. If I add together this and that at any point, you will always get the total energy. And I can see, for example, down here, I've got maximum potential energy. That's when the bob is right out on its swing, and zero kinetic energy, so it's not moving. Whereas this point, I might have maximum kinetic energy, but zero potential energy, and that will be in the middle point. Now, what we're going to look at after this will be damping and how these total energies start to decay, but I will cover that in a different lesson. So please do try the rest of the questions in that workbook. You should be able to attempt the energy ones now, and it should give you a bit more of an insight on how to solve some of the harder problems. Okay, thank you.